Hello, I'm Julia Kroll. I'm an applied engineer at Deepgram, and today I'll be talking with you all about minimizing request latency of self-hosted machine learning models. And I'll talk about what is self-hosting, how can you do it, and then how can you optimize it in production so that it scales at low latency. A little bit about myself first. I've contributed to global language AI products spanning dozens of languages. Earlier in my career, I worked on language expansion at Amazon Alexa, and now at Deepgram, I work on speech-to-text voice transcription, and we have models that support over 35 languages and dialects. Now, with a data science and machine learning background, a cheeky opinion on P99s is that they're outliers and should be removed accordingly. But I promise I won't do that in this presentation. We'll dive into those. An unpopular opinion that I have is that dark mode is overrated. I actually prefer Flux, which turns your entire screen orange so that you block out blue light. And another fun fact about me is that I brew my own kombucha. I have a gallon brewing right now. Now, laying out the foundation for this talk, I'll introduce two different concepts in machine learning. There's sort of two main tasks that you'll do in the space of machine learning models. The first is training models, and essentially that's allowing a model to learn by looking at lots of data that you show it. And then once you've trained a model, you use it for inference, which allows you to make predictions based on all of that past learning that has occurred. Now, both of these tasks require GPUs, but training is significantly more compute intensive than inference is. And I looked up some statistics to illustrate the discrepancy here, and I found an interesting one from Meta, where they're training the Llama 3 LLM on a GPU cluster of over 24,000 GPUs. And this will take still weeks to run. And on the flip side, if you're trying to use the open source Llama model to run your own inference, you can run inference for a request on a single GPU, or oftentimes, if you don't even care about latency, you can run requests on CPUs only. And so because inference is more focused on what we'll be doing in production in an application, that's what we'll be focusing on today. So what exactly is self-hosting a machine learning model? Assume that you have a trained model. As I mentioned, it's already seen tons of data. It has a pretty good understanding of the subject matter. And now you want to serve inference requests with the model. So you'll give it one piece of data and ask it, what do you think about this data based on everything you've learned? And you can use your own hardware to do this, either bare metal or cloud VMs. Now I'll go over a few different types of models that you can and can't self-host. There's a few different varieties that you can self-host. The first is open source models like Llama, Falcon, or Mistral, as well as a variety of models on Hugging Face. Now, because these models are open source, you can actually look in detail, you can see the model weights, you have a lot of detail on how they've been trained, and then you can also run them yourselves. There's another type of model that's encrypted and distributed, and this is how Deepgram's models work. Where we do the training, we don't surface all the details of the model weights, but we still provide you those models, we distribute them so that you can run them yourself. And finally, the third category is a model that is privately trained by you. You may have proprietary in-house models that you've developed on your own production data, and so you're not even exposing the model itself. You're just training the model internally and then hosting it for your customers. And then finally, the type of model that you cannot self-host is any model that isn't distributed. A few examples of popular models in this category are GPT, Gemini, and Claude. And you can make requests to these models. They have an exposed API that customers can use, but no one can actually get their hands on these models. You just have to use it through an API interface. Now, once you have a model that you can self-host, how do you actually self-host it at scale? Typically, this involves some kind of containerization via Docker or Kubernetes. And the way this works is that each container has a copy of the model that you're serving, and each container serves some inference requests. And you may be able to scale to more or fewer containers as needed, depending on your traffic. Now I'll go over a few different pros and cons of using a hosted API versus self-hosting. On the side of a hosted API, that's kind of the entry-level default. So it has some pros like you don't have to think about it. You can just make an API request and get a response back. It's very abstracted, and most of the time it just works. However, cons on the flip side are that you lack control and it may not suit your needs. And if it doesn't suit your needs, you don't have the ability to make any changes or troubleshoot behind the scenes so that it works better for you. It also may not scale if you have a large volume of traffic. It's expensive because it actually abstracts away a lot of the costs, both of the hardware that the model is running on and of the engineering effort to maintain the API itself. And finally, you're sending your data to a third party. When you're sending that data point to have inference run, the third party has to receive your data in order to run that request. Now, on the other side, if you self-host a model, you can control everything and you can trick out your perfect setup so you can make any adjustments you like. It's a custom-built solution. It's also very low margin because everything is internal to yourself or your company. You're not involving the labor or hardware of other companies. And critically, you retain your own data. So it's a very popular option for situations where the data is sensitive and where you don't want to send it to a third party. A few different industries that might fall into that case is with financial services or healthcare, where there's a lot of regulatory compliance restrictions. However, there are some cons to self-hosting. The largest one is that you're responsible for everything. You're maintaining a production service that backs all of your traffic, and therefore it takes engineering time and effort. You may need to have a larger engineering team in order to self-host a model rather than just use a hosted API. And then finally, a challenge for myself coming from a cloud computing background is you might have to remember that servers exist in the physical world. You're actually running all of your own servers. That can have challenges with scaling. If you're running on bare metal, you have to have somebody to go into a data center and perform maintenance or install new racks. So depending on how you go about self-hosting, it can really be a significant undertaking, although it doesn't have to be. Now I'll do a brief demo to show how it works self-hosting Deepgram. And as I alluded to before, Deepgram is a voice AI company. We do speech to text and text to speech. And so I'll show you an example where I have Deepgram models on my own EC2 instance. It's a G6 2XL instance, so it has one L4 NVIDIA GPU. That's a relatively new GPU type that came out in 2023, and I found that it's a really powerful, great instance for self-hosting models. And I've recorded about a 15-second audio clip that I'm actually going to stream through the model, and it's going to transcribe that audio, and it will show the JSON response that I'm getting back from my own model inference, as well as just the text transcript that's being transcribed. Now I'll go ahead and play the audio file so that you can see in advance of it being transcribed. Hi, this is Julia. I'm recording my voice, and I'm showing now for the conference demo how I can stream my speech into Deepgram's models and have it transcribe everything I'm saying in real time. So I've switched over to my terminal here. I'll do a sudo docker ps. You can see I've got a few containers running here. So I have an on-prem engine. That's actually the engine that's serving the ML models. I have an API. That's the kind of front end on the container, being able to receive requests that will pass them to the engine. And then I have a license proxy, which is just checking in with Deepgram so that Deepgram knows how much traffic I'm running. And I've got a Docker Compose file that spun up all of these containers. So there's kind of a default template that we provide so that you can launch a few containers. And now I'll use a Python script that I've got that's going to pass in my audio file that I just called Julia Sample Speech, and it's sending it to my local Nova 2 model. And I'll show you running this, that we're connecting to a local host. So this is running right on my machine. And you can see that every few seconds here, it's finalizing a result for transcription. So I'm actually running right on this EC2 instance, this machine learning model that transcribed that brief audio file. So now that you've seen how it works to self-host a model, I'll talk through a few different considerations for self-hosting in production. And this gets into a lot of those latency requirements where it's pretty easy to conceptualize of hosting a single model, playing around with it, making sure that it works in a simple case. But then it can get more complex when you're trying to actually scale and handle a production scenario, where especially if, for instance, in a streaming or low latency application, you have to be really sensitive to how long each of those inference requests will take and what's the overall traffic capacity. So I'll go over 3 questions that you can ask yourself to make sure that you're designing a low latency self-hosted model. The first is figuring out how many requests you can serve on your compute. Each server has a maximum level of traffic that it can serve before it falls over. It may hang, it may error out, but you don't even want to get anywhere close to that because latency will likely degrade before total failure. So the best way to determine a threshold of how many requests you can serve is to define the minimum acceptable latencies for your system, and you may define a P50, a P75, and a P99, that kind of thing. And then you'll benchmark to figure out what is the maximum number of requests that you can serve on the hardware you've selected. And then you can set limits in production. You'll be monitoring your traffic. And whenever you get too close to those limits, then you have the choice to scale up and to prepare to handle that level of traffic in a low latency way. Now I'll show you a concrete example of this. These are 2 screenshots that I've got from 2 different EC2 instances. One of them on the left is a G4DN.2XL that has a T4 GPU, which is a little bit older, not top of the line. It came out in 2018. And then on the right, I've got a G6.2XL. That's what I used for the demo. It has that L4 GPU that came out in 2023. And this is a terminal UI that we use to benchmark models. You can see the x-axis is in seconds, so it shows the last 10 seconds. And then on the y-axis, you've got latency going up from 0 to 600 milliseconds. Remember, this is in a real-time application, so latency that we're looking at is in the range of hundreds of milliseconds. And I've set up some metrics here for P1, P50, and P99. So you can kind of see the full distribution of request latency. And I've sent on the left N requests to this G4DN instance. And this is pushing the limits of this instance P99 is 560 milliseconds, which is definitely on the higher side if you're trying to build a real-time application. And even worse, you can see that it's kind of spiky over time. It's fluctuating between more like 300 to 560 milliseconds. So that's showing that it's kind of getting to the upper limit of this instance. However, when you compare that to the G6 on the right, I'm serving 2n requests on this instance. So double the level of traffic, but it's a more powerful instance. So double the traffic on this better instance is actually yielding a P99 of 360 milliseconds. And there's a smooth P99 over time, showing that this instance isn't being pushed to its limit. And so I show these two examples to emphasize that when you're self-hosting models, it's an extremely important variable just defining what compute you're using, because two instances that may seem pretty similar on paper can have a dramatically different amount of traffic that they can serve. So if you decide you're going to use all of one particular instance type or a mix of instance types depending on availability, you need to be able to have benchmarked beforehand how much traffic can each instance serve. Then extrapolating from there, you need to know how many servers do I need. When you know how many requests one unit of compute can serve, then you can extrapolate out to define the baseline, minimum and maximum, and it typically has daily or weekly periodicity. For instance, it's really common for requests to be higher during weekday business hours and lower on the weekends, but your business may have different periodicity than that. And then you can scale on the number of requests given the maximum requests for acceptable latency. And for instance, in Kubernetes, you would do this through a horizontal pod autoscaler. For instance, you might define that you can serve 100 requests maximum on a pod, and then you'll set the target ratio to 0.9. And then once the active requests become 91, that will give you a utilization ratio of 91%, which is over 0.9, and that will enable you to scale up to prepare for an increase in traffic. Then finally, you can ask yourself the question, which set of models am I serving? For low latency inference, models have to stay in memory, so there's a few different considerations here. You have to decide, are you serving one model, a few models, or many models? And then you'll have to look at how large are your models and how much memory do your instances have. And it's actually very common in a production ML case that you don't just have one model, that you fine-tune dozens, hundreds, maybe even thousands of models. And so it can be a real challenge in ML ops to determine how are you going to serve these all and what is your infrastructure going to look like. And I'm going to walk through a few different scenarios here. These are using Deepgram's language models, where we actually have one model per language that we support. And so when I hosted a low level of traffic with just one model, it was very responsive. P99 was under 100 milliseconds, which is incredible latency. And that worked very well. Now, when I moved up to 5 models, it was straining the system a little bit more. P99 was up to 800 milliseconds. And you can see I've adjusted the y-axis on these graphs since last time to be able to reflect that. And then finally, I was really pushing the instance. I put 15 models and distributed requests across those different languages. And that got up to a P99 of 2,000 milliseconds. And so with 2 full seconds, you've really failed in your real-time application. And so that shows how there's really memory constraints and the system isn't working well. So to serve as many models with low latency, make sure that you have several servers, each with a subset of models, and then you can load balance to distribute traffic across those servers. And you can send each request to a server containing the right model. So you have kind of a web that you've set up so that you can serve a subset of the traffic on each instance and kind of scale horizontally in that way. So in conclusion, for low latency self-hosted ML inference, first you'll select your models, then you'll define and benchmark your request limits, you'll auto-scale on those known limits, and then finally you can distribute many models and their requests across a fleet of servers. That concludes my talk. Thank you all for listening. Feel free to connect with me over email or on LinkedIn.